Welcome everyone. I'm Tony Waskilly and I'm a Professor of Energy Systems and Co-Director of Durham Energy Institute at Durham University. This is the second day of our 4-day Net Zero Research Conference. The first 2 days of this conference are structured around the themes of Network H2, that's the Network for Hydrogen Field Transportation, which is funded by EPSRC and led by myself at Durham University. The network brings together researchers, companies, governments, and other stakeholders across the UK and interacts with internationally leading organizations and researchers across many different countries in the transport field. The structure of the network is around 8 cross-cutting themes. Firstly, on whole transport and energy systems and the interaction between them, pathways to sustainable hydrogen production and its distribution, compact and lightweight hydrogen storage, and more compact and lightweight onboard hydrogen energy conversion devices. Also on improved lightweighting and efficiency of electrified powertrains for transport applications, hydrogen compatibility of materials and their safety. And the final 2 themes are on multimodal transport, logistics and autonomy, and policy, economics and societal impact. So EPSRC funds this national network, as I mentioned, and has been awarded to us to allow us to act as a forum to maximize impact from the research that they fund and the research that UKRI fund, and to communicate and share best practice and disseminate information and data all around the theme of hydrogen field transportation, and that's all transport modes. Also to capture state of the art and identify the research challenges from that exercise and examine ways to incentivize and look at the barriers that exist to the take-up of hydrogen for transport. We also have 50% of our funding to support new research programs, so funding cross-cutting projects to unlock research on hydrogen transport applications. Also, we aim to provide a wider forum for all stakeholders, again, for all modes of transport and technology developers, and to foster long-term collaborations between outstanding international research teams. And finally, to engage with the wider research community across the physical sciences, social sciences, and engineering disciplines to maximize dissemination and impact of the research outcomes and to stimulate knowledge transfer between academia, industry, government, and other stakeholders. So over the 2 days, we are looking at the challenges across different forms of transport, as well as developing the supply chain to support this hydrogen transition. So today is organized in 3 parts. So we're now entering into session 1, which will look at hydrogen production and distribution. We will then host a net zero question time panel with questions provided by the attendees. And then after lunch, we will resume with a session looking at storage and conversion. We have asked each speaker to present for around 20 minutes. And once they've finished, we will open up for a Q&A session. So without further ado, we'll move into the first session, and I would like to introduce our first speaker. So Dr. Valerie Dupont is from Leeds University. Valerie is a reader in low carbon energy and a co-I for the Center for Research into Energy Demand Solutions. She has been conducting research into near zero emission combustion and the sustainable production of high purity hydrogen, syngas and methane through advanced reforming processes. So over to you, Valerie.
Thank you, Tony. This is an overview on hydrogen production. So don't expect a lot of details, but more general stuff. So my talk is going to be structured first around world hydrogen production and uses. And then we'll be looking at in a very general way, the hydrogen production technologies, their pros and cons, what's happening now, what may happen in the future. And then we'll go a little bit more deeper into the current reforming technologies and looking at captive and merchant hydrogen. And then we'll do the same with electrolysis technologies, and we'll finish this with what we're going to do for net zero in the future. So currently, annually, we are needing roughly 65 to 102 million metric tons per year of hydrogen as a commodity. It's a wide uncertainty because of the definitions of the different hydrogens that exist. So there is merchant hydrogen. This is the hydrogen that is sold from a production plant to a consumer, and then is delivered by pipeline or bulk tank or by cylinder truck. And then there's the captive hydrogen. Captive hydrogen is something people tend to forget about. It's hydrogen that is produced on site and used on site. So it doesn't leave the plant where the hydrogen is produced. And then we have also the concept of byproduct hydrogen. And byproduct hydrogen is when it's made by a process whose main aim is not to make hydrogen, but something else. And the hydrogen is recovered. And this can be either captive or merchant, but generally speaking, the byproduct hydrogen is captive, meaning that it will be reused internally by the plant. So if we look at the split into the current uses of hydrogen, why we need hydrogen at the moment, and you need to think about, well, where will transport fit into this current picture? You'll see that the 53% of the hydrogen produced is used for ammonia production. Ammonia is mainly, overwhelmingly needed for synthetic fertilizers. The second main contributor for the uses of hydrogen is refinery uses. And the refinery uses, there's a lot in there of the captive hydrogen, because refineries have stages in their unit operations that generate hydrogen, but they also have other stages where they need a lot of hydrogen. And very often what happens is that in refinery, they can't generate enough hydrogen for their own needs, and therefore require also topping up with merchant hydrogen for their own uses. And we'll see a little bit more about this in the next slides. And then there's 7% that is specifically used for methanol production, and then 20%, which is other various uses. So we have to think that if we're going to start to use hydrogen for transport, we have to enlarge this 20% of other and fit in the transport needs. Now, if we look at the split between merchant hydrogen, the one that is available for buying, and captive hydrogen, the split is overwhelmingly biased towards captive hydrogen. So a lot of the hydrogen that we're making globally is used on site, and is used on site very often for these two purposes of refinery operations mainly, and then ammonia. My values here of captive 55 million metric tons per annum of hydrogen being produced, and that compared with a much smaller amount of 9 million metric tons of merchant hydrogen. So again, if we're thinking about expanding the transport chunk, we need to think about this balance of merchant versus captive hydrogen to be really tipped towards merchant. So going back to this large chunk of hydrogen use as for ammonia fertilizers production, these slides show that the need for ammonia and therefore hydrogen to produce ammonia has been growing in tandem with the growth of the world population. So on the left-hand side, the figure shows that since the 1950s, this growth in population has been mirrored by the need for expanding hydrogen production for ammonia production. And what we have to think about is the future as well, how the continuous growth of population in the world is going to affect this continuous demand increase in hydrogen for ammonia production. So on the right-hand side, what we have is 2019 United Nations projections of population increase, which show that, you know, the middle line is the 2020 year. So what we're looking at is what happens after that. And we can see that Africa is overwhelmingly responsible for doubling the world population over the next 80 years or so. And other regions like Asia, India, for instance, developing countries are going to see their peak reached around 2070 something. So again, we have to think that we're going to compete with the hydrogen generated for fertilizers to maintain this population growth and food production, as well as their need for transportation in terms of refinery needs only, not just hydrogen as a fuel. So when we look at the sources of hydrogen, we probably all are familiar with the split of where these hydrogen sources come from. And we can see that 48% of our hydrogen comes from natural gas. And when they come from natural gas, the technologies that are associated with conversion of natural gas to hydrogen are reforming processes, look like steam methane reforming. And I'm connecting the left-hand side camembert figure to the right-hand side, which shows cost and energy efficiency of the different processes. So the blue arrow, which connects the natural gas, 48% source of hydrogen, is connected to steam methane reforming on the very left-hand side of my bar graph, which shows the lowest cost and the highest efficiencies. And then we have all sorts of other reforming processes like coal gasification, whereby coal is responsible for 18% of our hydrogen. Also pretty cheap and efficiency very good as well. All of these are obviously CO2 emitters, and that's what we have to get away from. In comparison, the electrolysis processes, which are tipped as our green way of making hydrogen, are responsible currently for just 4% of the hydrogen sources. And they're also associated with the highest costs and one of the lowest efficiencies as well. There's the large portion of our hydrogen source, which you can see 30% for oil, coming from oil. And this is typically associated with that captive hydrogen from refineries. And the process responsible for the hydrogen generation at refineries is catalytic reforming of naphtha. So the first photo that you can see below the camembert is a photo of a large naphtha catalytic reformer. And below that, you can see where inside the refinery, the hydrogen is then being used. So they're being used in hydrocrackers. They're used for hydrotreatment, meaning that you're reacting hydrogen with a semi-refined petroleum product to remove impurities like sulfur, metals, etc. And the main costs of running these hydrocrackers and hydrotreatments comes from the consumption of hydrogen, which is 84%. So this is why we have to top up very often captive hydrogen from refineries with merchant hydrogen. So looking at technologies a little bit more in definitions, you can produce hydrogen straight from water. We've seen this electrolysis. 4% of our hydrogen is the cleanest, but also the most expensive. And the efficiencies associated with electrolyzers vary according to the type of electrolyzer. So for alkaline electrolyzers, you'll see efficiencies of hydrogen production between 43 to 67%. These are electrolyzers that are heavy, and usually they are well used in stationary situations. So you're producing hydrogen in the same place, and then you have to store it, move it to wherever it's being used. So if it's used for transport, it have to be brought to the forecourt. For PEM, so these are proton exchange membrane electrolyzers, also called polymer electrolyte membrane electrolyzers. The efficiency is just slightly lower, but they're very light devices because their electrolyzer is made of a polymer. And what is interesting from point of view of transport is that they can be reversible. You can use the same apparatus to generate hydrogen, or you can use the hydrogen and generate power in the PEM FC, the PEM fuel cell. So that's why the PEM type of electrolyzers, from the point of view of transport, can be very interesting. Generally speaking, because the efficiencies are lower and the costs are higher, it's okay to have electrolyzers if you have abundant renewable power. So typically, offshore wind farms would be the main candidates for storing energy in the form of green hydrogen via an electrolyzer positioned offshore. The pros as well of the electrolysis process is that you have a very interesting byproduct, which is oxygen. People tend to forget that. Yeah, we have two products from electrolysis. And the oxygen byproduct is very valuable for operating energy processes that rely on an oxidant that is made of either oxygen-enriched air or just oxygen, like oxycombustion, or processes that are there to convert dirty fuels like coal, for instance, or biomass into syngas via partial oxidation. So both of these technologies, oxycombustion, partial oxidation, are very useful for carbon capture later on, because the fuels that are generated are not diluted with the nitrogen from air. So that's very useful when you are coupling hydrogen production with either a clean fuel production or a power generation process. And nowadays, we hear a lot about oxygen and oxygen demand by hospitals because of COVID-19. So there's particularly an oxygen task force, emergency task force that has been set up to deal worldwide with this very important need for delivering large amounts of oxygens in urban areas where respiratory diseases are booming. On the right-hand side, we have the typical PEM electrolyzer. So it's schematically, it's very simple to look at. You have water fed at the anode. The anode is positively charged. The water is again split up into a part which is oxygen, and then a proton, and the proton travels through the membrane towards the cathode. And at the cathode, electrons from a power supply are supplied to generate and convert the protons into hydrogen gas. For reforming processes, those are responsible for most of the hydrogen worldwide. What we're looking at is the conversion of the methane molecule with reacting with steam to make 4 molecules of hydrogen and carbon dioxide. That's the overall process. And it's very heat demanding. Its change in enthalpy of reaction is very positive. So it requires heat, it's expensive to run. This is actually split up in two specific steps, main steps. One of them is first step that generates carbon monoxide in the first place, that needs a lot of heat. But the second step, which reacts the carbon monoxide with steam again, is the opposite. It generates heat. So that's why they have to be separated. But overall, you get the production of hydrogen and co-product carbon dioxide. So there are other reforming processes that are around that will be important when we start implementing carbon capture at a large scale. And these are partial oxidation and autothermal reforming. These are processes that whose main reaction generates heat. It doesn't generate as much hydrogen than the steam reforming reaction, but the important thing is that because they run on oxygen rather than air as an oxidant or steam as an oxidant, the flues are concentrated in carbon dioxide and water. The water can be condensed easily, and then you can separate the CO2 and then store it permanently if possible. The thermal efficiencies of these plants is in excess of 70%, which is larger than the electrolysis. If we look at the heat demand of just splitting water per mole of hydrogen, the splitting water reaction requires 4 times more than the steam methane reforming process. So that's why you have this dominance of the steam reforming process. In the bottom part of the slide, you can see the captive hydrogen production. There's an example of how hydrogen gets generated through the catalytic reforming of naphtha. So this example is an N-heptane conversion to toluene plus 4 hydrogens. So this happens a lot. This type of reaction happens a lot within the refinery, and the hydrogen is then reused for the hydrodesulfurization, hydrodemeterization. So the problem with reforming technologies is that they have complex plants. They're complex plants that have been perfected, optimized over many, many years. So that's why the efficiency overall of the plant is large. But you have to take into account that every single stage has a reason to be. And so this is one of the diagrams that I thought was most complete in terms of showing everything that's needed in a steam methane reforming plant. You would find this typically either in captive or merchant hydrogen, because refineries can have their own steam methane reforming plants for the top-up. So first of all, we need steam, so that you have a demineralization unit that's at the top. That will then be fed into a boiler, which is or a cogeneration unit, whereby you can have both generation of steam required for both the pre-reformers, the reformer, and the water gas shift stages, where hydrogen is being generated, and also power from the steam excess. And then we have the natural gas feedstock. This natural gas contains some C2 and C3 species. That's why we have a pre-reformer then that converts all the C2 and C3 species into methane. The reason being that the reformer catalysts cannot cope very well with the coke that would be formed if those C2 and C3 species were still present. So it's really a way of making the reformer run well. And in the reformer, you have the steam reforming reaction that happens. You have a lot of CO and hydrogen generated. And then that's followed by the water gas shift stage at lower temperature, because it's an exothermic reaction. So that's why they're separated. Now, this gray box around the reformer is a furnace. And maybe you can't see that, but there's a recycle that shows after the purification stage, which is here a pressure swing adsorber that conducts the off gas of the purification stage back into the furnace and burns there for providing the heat necessary for steam reforming. So I got ahead a bit of myself with the pressure swing adsorber. Once we have the water gas shift product, which is hydrogen and CO2 mainly, but also unreacted methane, because you have to think that these plants are run at high pressure, medium high pressure, and that's not good for the conversion of the methane. There will be also some leftover methane left in there. We have to extract the pure hydrogen, and this is done via a multi-bed adsorption process that changes the pressure back and forth to enable the hydrogen to flow through and the impurities to be diverted. These impurities will contain rather a significant amount of the product hydrogen itself, as well as unconverted methane. So all this is flammable, and that's why it's recycled to the furnace. And then finally, you have an expensive stage, which is the hydrogen compression. These are examples of the furnaces that are holding the reformers. And as you can see, these are very stringent conditions, very high temperatures, whereby tubes that contain the catalysts are in the center of the furnace, And you'll see how this happened in the tubes. These are very long tubes, typically 14 meters long, just over 10 centimeters diameter. They're filled with those ceramic coated catalysts or impregnated catalysts that are usually made with nickel and alumina. And the problems with these large plants is that if you have a power outage, the very, very expensive tubes can break. And that means either condemning the tubes or replacing them. They're extremely expensive. And their material are made to resist very high temperatures normally. Another issue with SMR is the amount of carbon dioxide that's emitted. So for 100 million metric standard cubic feet of production of hydrogen, the typical emission of CO2 associated would be around 9 kilos of CO2 per kilo of hydrogen. For electrolysis, we have typically 3 types of electrolyzers: alkaline, solid oxides, PEM. So alkaline solid oxides are large, heavy, bulky things. They're associated with stationary production of hydrogen. The PEM water electrolyzers are the ones that we think are more for the future of transport. And so you would see that their typical elements present would be the PEM cell stack, which is in picture B, and the cell stack components, which are anode, cathode, bipolar plate, electrolyzer. The costs of these PEM electrolyzers are split, and you'd see that the highest cost comes from the stack, and within the stack itself, you'd have the cost associated with the separator plates, but overall there's kind of spread of the expense of the PEM electrolyzer. So in the future, what we envisage is that for green hydrogen generation, ideally you want this to be done without CO2 emissions. So that would be from a renewable source, and a large renewable source, so that we can benefit from economies of scale. And therefore, for us in the UK, where we have abundant offshore wind, then you have to think about offshore wind coupled with electrolysis platforms offshore, which would run with a water purification unit using the water supply from the sea. And then the generation of hydrogen and oxygen would be kept momentarily underground. The duration of this underground storage and the frequency of the periodic offloading will affect the cost later on of the whole plant. CapEx and OpEx. So when we look at studies that have considered such setups, the net present value for 2 days storage would become positive at around the 8th year for a 35-ton production. And you can see that on the tanker of this diagram, there's the oxygen as well. So the oxygen can then be used onshore for power generation, clean power generation with carbon. And these are the most promising of the reforming technologies that are coupled with zero carbon or low carbon, meaning that they would run in tandem with carbon capture. So in this graph, which is from a recent publication of 2020, we can see that the most promising reforming technologies are those that are run on autothermal reforming coupled with carbon capture and storage. So these show that they have the lowest emissions of CO2 compared to, for instance, the steam methane reforming plants. So this means that the new plants we're going to build for hydrogen production for the higher demand of transport are likely to be autothermal reforming rather than steam methane reforming because of this facility with carbon capture. I think I should stop now, and that's it. Thank you.
Thank you very much, Valerie, for a very interesting presentation. We'll move on. So we're moving from production now to distribution. So our next speaker is Dr. Danielle Stewart from National Grid. Danielle is the long-term strategy manager, where she supports and develops innovation projects on zero or low carbon sources of energy. She is currently leading the development of a collaborative program of work to build the evidence base for hydrogen technology as a cleaner alternative to natural gas for use in homes, industry, power, and for transport. So over to you, Danielle.
Thank you, Tony. So good morning, everybody. Thank you for the invite to come and speak today. I'm very pleased to be here. Today, I'm going to speak to you about hydrogen and gas networks, so specifically the gas transmission network, but I will touch on gas distribution as well. So we'll make a start. So I want to start by talking about the role of gas in the UK today. So natural gas has a central role to play in the UK's energy system. It heats around 85% of our homes today and serves around 22 million customers. And around 40% of our gas goes to generating power, around 38% for our industrial consumers, and 23%, the other way around, 23% goes to our domestic consumers. So to give you an idea of the scale of the decarbonisation challenge, the gas network transports almost 3 times as much energy per year on average when you compare to the electricity wires. And on a cold winter's day, you could see as much as 4 to 5 times that energy. So creating that more sustainable energy system is one of the greatest challenges that the sector faces today. Now, for those of you who aren't familiar with National Grid operates gas and electricity networks in the UK and the US. In particular, I'm going to talk about the UK's gas transmission system. So the transmission system consists of around 7,660 kilometres of very high pressure pipelines. So they operate between 38 bar right up to 94 bar. We have 23 compressor stations, so I think this slide needs updating. We have 8 gas terminals, and we're connected to the rest of Europe via pipeline interconnectors to Belgium, Netherlands, and Ireland. So I just wanted to set the context, and I'm sure many of you are familiar with it. But since the announcement in June 2019 that the UK is committed to a legally binding target of net zero greenhouse gas emissions by 2050, and of course 2045 in Scotland, we've really started to see an increased focus both from government, industry and academia on the energy transition. And we had a whole host of policy announcements in this space just before Christmas. So we had the Prime Minister's 10-point plan, we had the Energy White Paper, Scotland's Climate Action Plan update, Treasury's interim net zero report, and of course the Climate Change Committee's recommendation to government for the 6th carbon budget, which we've just seen this week has been enshrined in UK law. Over the coming months, we're expecting the hydrogen strategy and a heat and building strategy in the lead up to COP26, which is the global international conference on climate change. But I just want to draw attention to the Prime Minister's 10-point plan and some of the policy aims for hydrogen in there. So within that plan, there's an ambition to have at least 5 gigawatts of hydrogen production capacity by 2030 in partnership with both industry and wider industry. So in a high hydrogen scenario, government estimates that it could see the UK benefit from around 8,000 jobs by 2030 and up to 100,000 jobs by 2050. So to support this, they've proposed a range of measures, including a £240 million net zero hydrogen fund. And we'll soon see business models to support more private investment in this space too. By 2023, and this is of particular interest to the gas networks, they're aiming to have testing completed to allow up to a 20% blend of hydrogen with natural gas into the gas distribution grid. And they also want to see a large hydrogen village trial by 2025 and a hydrogen town by 2030. So all of this shows that the government is really serious about hydrogen. And in all credible analysis to reach net zero, there will need to be some level of hydrogen in the economy. Different analysis talks about different amounts, but there is always some level. So in this respect, the gas networks really need to understand if and what their role could be to help facilitation of this hydrogen economy. And over the coming slides, I want to talk about some of the work that the gas networks are doing, and in particular gas transmission. So as you can see from this slide, there's a huge amount of work happening across the UK at the moment looking at hydrogen. And not all of it is run by the gas network, so there are some things on there that are outside of that, but we are particularly interested as we sit right in the centre of that value chain. So I'm just going to talk through some of them. So Future Grid, that's National Grid Gas Transmission's offline hydrogen test facility. So I'm not going to go into detail on what that is just now because I'll speak more on it in a couple of slides' time. There's the Zero Carbon Humber project, which is a collaboration between National Grid Ventures, so our commercial arm, Drax and Equinor, looking to decarbonise the industrial cluster in the Humber region. So the project includes low carbon hydrogen production, carbon capture use and storage, and shared onshore and offshore infrastructure. There's also Project Cavendish, So that's looking at the potential for using existing infrastructure in the southeast and around the Isle of Grain region to supply hydrogen to London and the southeast. In the scope of the project is generation, storage, transport, and carbon capture and storage. Gas transmission was involved in the early studies, but it's now National Grid's commercial ventures business that's leading this. And Cavendish is looking at around about a 700 megawatt blue hydrogen production facility to be in operation late in 2026, with the potential to grow that to up to 1.75 gigawatts of production by 2030. So the project is really anchored around demand from the local power stations, and they're proposing to blend up to a 20% mix of hydrogen into the natural gas fuel supply. It also has the potential to blend into the transmission and the distribution gas networks for heat decarbonisation. There's also the ACORN project. So ACORN is a collaborative CCS, a carbon capture and storage project, and hydrogen project in Scotland, run by Pelblue Energy. And that's looking to be in operation by mid-2020s. It aims to produce blue hydrogen at St Fergus Gas Terminal, as well as reusing some of the existing oil and gas pipelines on and offshore, and particularly looking to store CO2 offshore. So the project looks to blend hydrogen with natural gas into the gas transmission network again, and starting with a 2% blend and potentially growing that up to 20%. There's also the High Deploy project. So if I start with High Deploy 1, that's led by Cadent, so one of the gas distribution networks in the UK, in collaboration with Northern Gas Networks, Keele University, the Health and Safety Executive, ITM Power, and Progressive Energy. And it's the first project in the UK to blend hydrogen into a natural gas network. Now, phase 1 has recently been completed, having started in October 2019, and it's taking place on a private gas network at Keele University campus. And it's currently been safely supplying a blend of up to 20% hydrogen by volume to around about 100 homes and 30 university buildings. And during the trial, customers at Keele have used hydrogen blended gas safely in their homes and without the need to make any changes to their existing appliances. And we're expecting a full report on that later this year. Now, High Deploy 2 is the next phase, and that will begin a larger blend and demonstration on a public gas network with more than 650 homes later this spring at Winlayton at Gateshead, subject to final approval by the HSE. And there's also H100 Fife, so that's SGN, so another gas distribution network, their project in Scotland, and it's developing a world's first hydrogen network in Levenmouth that will bring 100% renewable hydrogen through a purpose-built network, and that will go to around 300 homes by 2022. There's also H21, so that's another collaborative project between the gas distribution networks, DNVGL and the HSE, but this time it's led by Northern Gas Networks. And really it's a suite of projects designed to support the conversion of UK gas networks to carry 100% hydrogen. And I should mention as well, there's also the High for Heat project. So this is a BEIS-led initiative to really establish if it's technically possible, safe and convenient to replace natural gas with hydrogen in both residential and commercial buildings, as well as gas appliances. And this will really enable government to determine whether or not they want to proceed with a community trial. So I'm just going to focus now a little bit more on what National Grid Gas Transmission is doing. So our HINTS programme, or High NTS, that's the banner that we've used for all of our hydrogen innovation projects. Now on this slide, you can see a number of completed projects, so I won't spend too much time here. And I've already mentioned Project Cavendish, so that's the project in the southeast in the Isle of Grain region. Aberdeen Fission was an early project before the ACORN project, and it was a feasibility study looking at the generation of hydrogen at St Fergus in Scotland, so one of our gas terminals, using the NTS, so the National Transmission System, and blending around 2% to supply the city of Aberdeen. We've also carried out a feasibility study of hydrogen in the NTS, so that was working with the Health and Safety Executive Science Division, and that was a desktop study looking at whether or not we believe it's possible to transport hydrogen in our gas networks, and in particular looking at the impact of hydrogen on the steel pipelines. So technically it's believed it's possible, but there are a number of things we need to do, and there are a number of caveats that came out of that report. So in particular, we need to run a physical trial, but also we need to understand the integrity of some of our assets and our pipelines. And also there is a concern that many people have around embrittlement of steel. So one of the suggestions is that we may be able to prevent steel embrittlement by doping with a very small amount of oxygen into the hydrogen supply itself. We've also been looking at hydrogen injection projects, so looking at where there might be a good place to inject hydrogen onto our network for trials. We've had a hydrogen flow loop looking at metallurgy changes for 30% hydrogen on some of our pipelines. And we've also got a hydrogen deblending project. So we've carried one out. We're about to do some more work in this. And this is really looking at technology that exists today, but has the potential to separate hydrogen from natural gas for those consumers who potentially aren't ready to transition to hydrogen or a blend at this point in time. So it's a techno-economic study that we've been working on. So now I think it's worth talking about our Future Grid project. So Future Grid is our flagship project that we've got at National Grid at the moment. And it's all about building an offline test facility at Spade Adam in Cumbria. And we're taking a range of decommissioned, so redundant assets from our network. We're taking them up to Spade Adam and then we're connecting them together to build a mini transmission network. Now, the project has been funded under the Network Innovation Competition, and that is a funding mechanism for innovation works under Ofgem's regulatory price control for RIIO-1. Now, the project's just about to start this month. It's a 2-year project for phase 1, and that's what we have funding for. And it's looking to understand the impact of a 2% blend, a 20% blend, right up to 100% in our gas assets. So that's that particular project, but alongside it, Northern Gas Networks are also building a distribution network offline test facility. And alongside that, there are a number of houses. So there's 3 houses been built at Spade Adam that have hydrogen appliances in. So it may be possible to connect us all up and run a full beach to meter setup. Now, I should also mention our project partners. There's 6 project partners. DNVGL are our main delivery partner, and they're responsible for building the test facility and developing the master test plan across the range of assets. The HSE are involved. The Science Division are supporting the development of the test facility too, and the subsequent test plan, providing that technical assurance and validation. Northern Gas Networks, as I mentioned, they're building their distribution network, so they're partnering with us. Fluxus are also partnering with us, so they're the equivalent of gas transmission in Belgium, and they're contributing a substantial level of hydrogen research to ensure that real international collaborative approach. And we're also partnering with Durham University and the University of Edinburgh too. So just to give you an idea of some of the assets, I won't spend much time on this, but we have an entry point, we have a block valve, a pipeline and an exit point, all as part of phase 1 of this trial. And the exit point allows us to either recirculate gas around the test network or redirect it to NGN's distribution facility. And as I mentioned before, these assets are coming from all over our network, so really are truly representative of the assets. Always good to show a picture. So for anybody who's interested in the houses, they look like normal houses. They are at the test facility. This is a photo of them on the high street. It's part of the High for Heat programme, which is a programme being led by the Department for Business, Energy and Industrial Strategy. And they've been testing hydrogen safety within the home. And just to give you an idea of the scale and the layout of the site, the big red strip is where National Grid are proposing to build their offline test facility. So that's the Future Grid facility. In the middle of the slide, you can see H21, which is where NGN's distribution facility will be based. And then you've got the high street, which is where those houses are located. So as you can see, it's quite a large scale project. Now, I mentioned phase 1. That's everything I've been talking about so far, but there are a couple more phases that come after this. We're also looking at deblending and compression. So that's part of phase 2. So for anybody who noticed, compression wasn't part of phase 1 in the next couple of years. But from 2022, we'll be starting to set up all of the assets to be able to test compression and deblending that I mentioned earlier. Finally, in phase 3, we'll have third-party testing. So we'll open up that facility for anybody who wants to test some of their assets, further collaboration, and potentially also using it as a training facility. And alongside this, we're also considering where we might be able to do online trials with real consumers. Another one of our key projects through the next 5 years, so our regulatory period and beyond, will be Project Union. So Project Union looks to review the potential for a phased repurposing of transmission pipelines to create a UK hydrogen backbone. And that aims to connect the UK's largest industrial clusters. And industrial clusters are typically located at the coast, and you should be able to see them on the slide here, alongside their current emissions. So the largest clusters are highlighted here. Now, there's a number of benefits to connecting them. We believe that early scale-up hydrogen could come from these clusters. Now, connecting them could provide resilience. Where there's a potential for excess hydrogen generation, it could transport hydrogen to different demand centres. Could stimulate the market for hydrogen too, so it's somewhere for hydrogen producers to put their gas and it connects them to consumers. There's also early decarbonisation opportunities for customers connected to those pipelines outside of the clusters, so it's not just for people in the clusters. And there's also clearly learning for a wider rollout, should that be the direction that we want to go. Now, there are a number of potential pipelines we're considering, especially where there may be duplicate pipelines, but we do need to carry out a lot more analysis to understand the impact of removing these from the natural gas network and also to understand the right ordering of them. And we've been looking at advancing some of our simulation software to be able to carry out a lot more analysis in this space. So it's not just about answering all the asset questions, and I should mention this too. So there's a number of enablers that need to be considered, such as the markets and the commercial arrangements to enable hydrogen onto networks. And I want to mention one of them here. So the gas markets plan. So through the gas markets plan, or GMAP as it's sometimes known, National Grid is taking a lead role in how the gas market needs to evolve as that gas that's supplied is used and changed in different ways. So through extensive stakeholder engagement and through our Future of Gas Forum, 3 focus areas have been identified to inform the market changes that are going to be required over the next 2 to 10 years. And that's gas quality, balancing, and hydrogen. So our stakeholders have really highlighted that hydrogen is a priority for us. So we will be considering the possible market rules given the potential production methods for how hydrogen could integrate with natural gas and its end uses. And I think it's also important just to talk about collaboration. So we're not doing this on our own. It's not just the UK, and nor is it just National Grid. We are collaborating with wider industry and government in the UK as well as Europe through a number of fora. And that allows us really to engage with the wider community, share our knowledge, inform policy, and do it in an efficient and coordinated way. And since launching Future Grid, we've had more and more people coming to us wanting to work with us. So that's great news. So I just want to highlight some of the areas we are collaborating in. Some of you may or may not be familiar, but there's the Gas Goes Green project. So this is led by the Energy Networks Association, who are the trade association for gas and electricity networks in the UK. And Britain's 5 gas networks are all coming together to build that world's first carbon gas grid. So there's a number of deliverables that we are committing to. It started last year. We've just launched this year's deliverables. So if you go to the ENA's website, you can find out much more about what we're doing in this space. We're also working on the Hydrogen Grid R&D programme. So over the last year, gas networks have been working together with the Department for Business, Energy and Industrial Strategy to really build that collaborative programme of work to build the evidence base for hydrogen and gas networks. And the ultimate aim of this is to inform heat policy. There's a number of work streams covering the technical, the economic, as well as the logistical questions, answering some of the safety and the operational questions, looking at where trials might be carried out with consumers, and ultimately as well, looking at how you might transition from the network we have today to a hydrogen network of the future. Now in Europe, we're part of the Gas Grid Asset Readiness Group. So we're working with a wider group of 7 European transmission system operators as part of this group, H2GAR for short. And H2GAR really aims to contribute to the development of new standards and technologies that we're going to need in the future. It enables technical knowledge sharing, and it allows us to develop that common view on gas asset readiness as well for hydrogen. A number of working groups covering everything from pipelines, compressor stations, separation systems, metering, safety, as well as storage. So a lot going on there. And then the final place that I just want to mention that we're collaborating is part of the European Hydrogen Backbone Study. So in July last year, a group of 11 European gas infrastructure companies came together and they published a vision for how a hydrogen backbone in Europe could develop between now and 2040. Since that time, many more gas infrastructure companies have joined, including National Grid. So there's now 23 companies across 21 countries. And last week, we launched an updated version of these maps showing how, depending on how the markets develop, obviously, and policy develops and the regulatory frameworks, how it could look. So there are around 39,000 kilometres of high pressure pipelines been identified, with around a 69% repurposed network and a number of new pipelines as well. So just to finish off, very high level summary. So hydrogen could have a role to play across all sectors in the journey to net zero. We believe that we can repurpose our networks, but there's still significant evidence that we need to build. And in particular, over the next 5 years, that will be a really critical period for us. We know that collaboration is key, both technically, but also to align with our stakeholders' ambitions. And ultimately, we do need to take that consumer-first approach, so keep our promise of transparency and affordability whilst bringing consumers along with us. So I think I'm going to end there. Thank you very much.
Okay, thank you very much, Danielle. That's an excellent presentation.